Hello friends. We are continuing our discussion on exponential and logarithmic graphs. We've also talked about inverse functions. So if you didn't watch the preceding videos, you might want to take a minute, make sure you understand inverse functions and exponential functions before we talk about logarithmic functions and their graphs. So one thing we have learned is that we've learned about inverse functions. And the big thing for inverse functions, when we think about inverses, is we need to switch our x and y. Okay, so inverses is when you interchange and switch that x and y value. We also talked about exponential graphs. And graphing an exponential function, that's y equals 2 to the x. All right? So an exponential function graph looked roughly like this. Had a horizontal asymptote at y equals 0 and a y-intercept of 0, 1. Okay, so in this situation, we're going to talk about the graph of a logarithmic function. And you'll notice this guy right here, we have x equals 2 to the y. So when you compare this logarithmic graph and this exponential graph, what do you notice about these two? And that's that the x and y values are interchanged, which means we're dealing with the inverse of an exponential function. Okay, so let's graph this here. And so you'll notice I'm going to plug in y values to calculate x. X is equal to 2 to the y. All right, so let's plug these in. And I'll start with my positive or 0 values first. So x equals 2 to the 0. That gives us 1. So x is 1 when y is 0. So x equals 2 to the first. We get 2. We have an ordered pair 2, 1. And then we get 4, 2. And 8, 3. And if you remember the points that we got when we graphed our exponential function, you'll see that these are all the exact same points, but the x and y are switched, so they're the inverse ordered pair. And if we were to look at, say, plugging in y equals 10, well, that would be x equals 2 to the 10th, and 2 to the 10th is 1024. Okay, so we have some ordered pairs here, and we'll go in the other direction. Remember, when you're dealing with negative exponents, you have this reciprocal property. So 2 to the negative 1 is 1 over 2. So I end up with 1/2 negative 1. 2 to the negative 2 is 1 over 4. So we've got 1/4 negative 2. And x equals 2 to the negative 3 gives me 1/8. So I have 1/8 negative 3. What if I were to plug in negative 10? Well, that would be x equals 2 to the negative 10th, which is 1 over 2 to the 10th, or 1 over 1024. So I'm very close to 0 here, and I move down 10 spaces. It looks like I'm getting closer and closer to 0 with my x, but I'm never going to touch it. So if I think about graphing this, 6, 7, 8, I'm going to go down 3 and up 3. I'm going to plot 0. We've got 1, 0. We have 2 up 1 over 4 up 2 over 8 up 3. So we look at what happens between 0 and 1 here, right? We're getting closer and closer to 0 with our x, but it looks like my x is never going to be actually 0. So I've got 1/2, I go down 1, 1/4, I go down 2, 1/8, I go down 3. And when we get to -10, which might be down here, we're still right on the right side of my y-axis. So when I think about graphing this, we get something that looks like this. And what we want to notice is it appears we have a vertical asymptote. And that vertical asymptote is at x equals 0 along the y-axis. Remember, the equation of a vertical line is x equals a number. And instead of a y-intercept, we have an x-intercept. And the x-intercept is 1, 0. So let's talk about domain here. We've been talking about domain all semester. And so far, we've only had 2 rules we need to adhere to. We know that when we're dealing with a denominator, it's not possible for us to allow the denominator to equal 0. And when we are dealing with even roots, square roots or fourth roots or sixth roots, we know that the radicand, what's under the square root or the argument of the square root, we know that that has to be positive. You can't take the square root or the even root of a negative number. And those are our 2 rules. And so now that we're into logarithms, we have another rule. And you'll notice here, my graph, it's never going to go to the left side of that vertical asymptote. It's never going to cross over it. So what is our domain in this situation? And so we have a new domain restriction. My x values go from 0 to positive infinity. And notice I use a parenthesis on 0 and not a bracket because we can't touch x equals 0. It's going to get really, really, really close, but it's never going to touch it. It's always going to be 1 divided by some value. All right, so we have a new domain restriction here. And if we continue thinking about this, let's just connect what we did last few videos. This gray graph that we're looking at, this represents an exponential graph, right? Y equals 2 to the x. And this pink graph down here, this looks like what we just graphed. This is my logarithm. And it's a logarithm in exponential form. So we don't know a lot about logarithms yet, but we'll be talking about them soon. Essentially, what this graph represents is y equals log base 2 of x. So this is a logarithm, and this is what a logarithmic graph looks like. Continuing to connect the concepts, you'll notice we have an exponential function here. Okay, and we know all of these properties. We talked about them in our exponential functions video. But let's relate them to this new logarithmic function we're talking about here. So one thing we know, they look really similar. Here's my exponential function, and the inverse of an exponential is a logarithm. We talked about the base being bigger than 1. If the base is bigger than 1, the graph is increasing. And that's the same property for a logarithm. The base is bigger than 1, we end up with an increasing graph. If the base is fractional between 0 and 1, we're going to have an exponential graph that is decreasing, or a logarithmic graph that is decreasing. They are both continuous and they're both 1-to-1, but this is what's important. We want to think about that domain and range. So the domain of the exponential was all real numbers, and the range on that exponential had a domain or had a restriction. So look at the domain and range for our logarithmic graph here. And what you'll notice is that they are switched. Okay, we've switched our domain and range. And that is indicative of an inverse, because when you switch your x's and y's, you're switching your set of x's and your set of y's. That means you're interchanging your domain and range. Domain is the set of possible x's. Range is the set of possible y values. And then the other two things that are important for us to notice, this has exponential has a horizontal asymptote, where logarithmic has a vertical asymptote. And exponential has a y-intercept 0, 1, where logarithmic has an x-intercept 0, 1. So the main point of this, we're just connecting that a logarithm is the inverse of an exponential function. It's a different way of representing it. Logarithms are a way of counting by powers. Some could even consider a logarithm to be an exponent, just written in a different form.